Hello. So, to start, of course, we're not going to run everything on here on our real computer here. So, to start, we're a bit underprepared here. So, we're just going to download a Fedora ISO to run in a VM first. Okay, to download this. Okay, we have the downloading here. We actually downloaded the files ahead of time, so we can skip a bit of time here. Okay, let's just look here. Okay, we have the checksum and the ISO, regular ISO file, and the checksum file. And yeah, we want to verify this, of course, because obviously. And we'll do that right now with the official instructions. Okay, verify your download. So how do we do this? First of all, download the checksum file, regular thing, we already have it here. Then we download the Fedora GPG keys, usual thing, download the keys. Just call it here, and just to be sure we can actually look at the fingerprints for the paranoid in the audience, verify the details of the GPG keys here, and we need to scroll down to the Fedora 43 key that is here. Okay, C6E7, that looks good. So, okay, let's continue verifying. Okay, regular GPG thing, just verify the signature. Okay, yeah, good signature, seems fine. For the Rust fans in the audience, we can even use the fancy new Rust alternative, Sequoia. So we do the Sequoia verify -- clear text and then the signature file. And that one authenticated signature, that's good. So let's verify if the actual SSH in there matches. So we just copy the command from here. It says, OK, yeah, good. We can even, like this is OK, but we can even verify it by hand, just looking at the SSH. OK, 7268 and 7268, and that seems legit, so we can just normally boot this. We'll just use QEMU for now, and boot this. And there we go, and we can boot this. And welcome to 3933 to our talk, Design or Not Design, Practical Vulnerabilities in GPG and Friends.
Hi, cool to see so many of you here interested in the internals of PGP implementation. The Herald already kindly introduced us. We're Lexi and Liam. We play together for the same CTF team, where Lexi mostly does web challenges and I focus on binary exploitation. So you might legitimately ask yourself the question, what business do we have talking about cryptography? Well, cryptography at its core is, of course, the mathematics, the operation on elliptic curves, and the RSA algorithm. But to make cryptography actually practically useful, you need layers on top of that. For example, padding schemes and modes of operation. And even on top of that, you need to specify how your data is serialized and parsed, and things like how you store and exchange keys with others. There is another dimension to it. There's the specification, which needs to specify a secure protocol, and then actual C or Rust or whatever code needs to implement that specification without introducing security-critical bugs. The specification in our case is PGP, short for pretty good privacy. It's a set of RFC standards defining these things, packet structure and cryptographic specifics. And the most well-known implementation of PGP is GPG, the GNU Privacy Guard, which most of this talk is about. Just remember G for GNU, like actually usable software that implements a CLI and library that can be used. There are other implementations of PGP, such as Sequoia PGP, short SQ, which we'll touch on, and we'll also briefly touch on the non-PGP tools such as H for encryption and Minisign for signing. PGP is used in a lot of places, for example, signing and encrypting emails, as we just saw apparently, verifying downloads, just a dependency for a lot of things if you search for it, for example, package managers. And PGP is kind of a rich standard, and the attack surface we've looked at mostly are signatures, where we looked at are they parsed correctly and are they actually verifying the right plain text that they are showing you. There's an authentication identity part. You want to use the right key for the right user. You also want to decrypt the ciphertext, the right ciphertext, and encrypt to the right recipient. And then GPG as a actual CLI tool, a library written in C. Of course, there's a memory safety dimension to it, and a safe usage in whatever environments they're used in. So how did we get here talking about GPG? How did this research start? Lexi will tell you something about this.
Okay, so the thing is, everything started basically with cryptography nerd stuff. So for context, this is my PGP public key, and as you can see, maybe this references its own URL and things like this. I wrote this key partially by hand, and I did stuff like this. Or for example, if you pipe this key into GPG, it does this. It displays the trans flag and says trans rights. And basically, I like doing shenanigans with GPG. I genuinely like GPG and messing with GPG, but that also involved reading GPG code. And while reading that, I found some pretty big bugs, and from there, it just kept on happening. We basically just looked under the sofa and found everything. So the entire thing started with signatures. You might have seen this explicitly before. It's basically how to use PGP to verify that an email is authentic. Look for this text at the top, and then the classic begin PGP signed message string. So let's actually look at how these works. So for example, this is a PGP signed message. You might have seen actually this one before, but this entire thing starts with the header. This is the clear text start. Then there are some headers, for example, specifying which hash algorithm to use. And then there's the actual text. This is hashed and verified. And then there's the actual base64. This contains a PGP packet stream containing a cryptographic signature to verify this thing. But the thing is, what you already might have noticed where some attack surfaces, these headers are not explicitly part of the signature. So if we could just do a naive attack here, we can just try to inject things here because it's not verified. So if we do this, it says GPG invalid clearsign header. Basically, they are aware of this problem and do things against this. Even if we look at the code, for example, this line is passed by the function parse hash header. This passes the familiar hash SIH to 512, for example. They explicitly say this is for security reasons. The header lines are not included in the hash, and using some creative formatting rules, Mallory, so an attacker, could fake any text at the beginning of a document. But the thing is, they specify here, we only allow the hash header, and I got curious and read more code. And if we actually look at the code that calls this parse hash header function, it's the parse header line function, we have the expected call of parse hash header that parses the line and actually checks that there's nothing behind it. And directly after that is a comparison if the line starts with not dash escaped. And if it starts with that, it just approves it no matter what's behind it. So if we just have a message like this, for example, if we use the option that actually uses this basically just slightly changes how the message is formatted. If we just use this, it says you need GPG to verify this message. But the thing is, you can just put anything here, like creative formatting, and it will still verify. As we can see, it says good signature. So we already injected some text into the actual Clearsign message here, and this is not verified. But the thing is, it gets worse. The C enjoyers in the audience might have already noticed it in this slide. There is a bug already in this line of code here. And it is actually this. This is a char pointer. And a char pointer means this is basically a C string, and C strings are terminated by null bytes. The thing is, we can just put our own null byte here, and then the code just thinks the line stops here, so we can just put anything after this, and we have injected content into the signature again. And what they mean by creative formatting is the following. If we just inject content here, it looks like, OK, hash and then something inside the hash header. That probably wouldn't convince anyone. So what we can do is this. We just inject vertical tabs and carriage returns, because those are not new lines. But the thing is, if we just look what they do, the vertical tabs move it down, the carriage returns move it to the left. So it looks like a new line, but GPG doesn't parse it as a new line. So for example, if we just apply this to something practical, we have our signature here saying this is a signature from Cicada 301, if you know that, basically saying we are here at the 39th Chaos Communication Congress, find us here, and spoilers, they are not here, this is completely spoofed. But if we verify this with GPG, we see good signature from Cicada 3301. And if we actually look, yes, this is basically just a null byte there, and \l, \l, and \v. And this completely fools GPG, and thus this is a good signature. So basically, the impact is verifying clear text. Well, that's actually not changed yet. Basically, verifying clear text signatures is not really possible and can show attacker-prepended text in any clear text signature. We reported this 2 months ago, and it still is not fixed. Recommendations for the users here basically just use GPG versions that include a patch that we will distribute later. And for users, basically just avoid this kind of signature and use --decrypt, because that will actually show what content was just parsed and verified. And we also looked at some alternatives. We looked at the Minisign project. This is a that simple tool to sign files and verify signatures. It's supposed to be simple to use, secure, and minimal. And this is the Minisign format. It's genuinely very small in compared to the giant PGP RFC. But what I noticed is this trusted command line here, because there is something somewhat similar to like the clear text signatures in Minisign, because this arbitrary text that we can write here is verified as well in part of the signature. And turns out, C strings are hard, because this line is also parsed by a bit of C code. They actually, like just injecting a \0 doesn't work. But the thing is, they trim strings. So for example, ABC with a new line gets trimmed to ABC. ABC with a carriage return, a new line gets turned into ABC, because they also look for carriage returns. And if they find a carriage return, they just replace that with a null byte to basically end the string. But the thing is, what we can do is just use the original signed content, then \r, and inject more content, and then the \n. And if we just trim that line, that gets turned into signed, and the injected content is not actually part of the signature anymore. This was basically discovered the day after I discovered the first vulnerability, and even wrote the actual proof of concept in my bed while it was still on my phone. You can see the Android logo even on there. And this just works. If you just look at the file, it says not very trusted, and if you actually verify it, it says something completely different. So if you just look at the signature file, you wouldn't notice that there's something injected in there. So the recap so far, we can basically add anything to the top of PGP signed messages, and non-PGP C tools also make the same C mistakes as GPG occasionally does. But the question is, can we break signatures even further? And for that, back to Liam.
Yeah, I mean, the first thing is kind of a visual thing that's not enough to fool something like SHA-256 following the Fedora instructions. So let's explain the bug that we first saw in the video. For that, let's introduce 2 signature types. We talked a lot about clear text signatures before. We just have the plain text and then the base 64 encoded signature there. And then there are also full signatures, which have everything base 64 encoded. Internally, they are packet streams. And the important observation here is that you can convert any signature type into any other signature type. Especially, you can convert a clear text signature into a full signature. The next observation we have is that there can be almost arbitrary unparsed text up here. Back to our XKCD, we just look for this, but maybe exactly this. If we can just subtly break this first line, I don't know, a dash more, but the best thing you can do is like a bomb, like a byte order mark. Somewhere in the header is like an intentionally invisible character. It's not even suspicious, because some editors sometimes randomly insert this. If you, like for example, Notepad on Windows, if you save as UTF-8. And this will kind of make the whole thing up there, which totally looks like a full signature, be parsed by both Sequoia and GPG as a which totally looks like a clear text signature, be parsed as a full signature. Another small detail here to observe, it doesn't matter for full signature verification whether it says begin PGP signature or begin PGP message. So we can just swap it back to the default. And what GPG sees is on the left, and we, of course, including the SHA-256 tool that is recommended to use, see the clear text signature on the right. So all it takes for us is we need to find some signed message, convert it to a full signature, and then put basically an arbitrary message up there. That's the impact. We reported this bug over 2 months ago, and neither GPG nor Sequoia have a patch for this or have one planned, at least not communicated to us. And I guess the recommendation would be to never mix signature types, especially Sequoia, where you specify that this is a clear text signature that you want to verify, and it still verifies as a full signature. You should have strict parsing as an implementation, and I guess in the medium term, with all these bugs in clear text signatures, it might be a good idea to move towards deprecating them. For users, again, also avoid using clearsigs. Then we would love to recommend to you to always use --decrypt to see what was actually parsed and trust this output. However, the next bug kind of goes against this. In this case, we have a third signature type, called detached signature, which is kind of the thing that is most recommended to be used, where the message and the signature are in two separate files. The message says hello 39C3, and now if we would decrypt this, we see the string malicious there, which was inserted by our proof of concept without needing to resign. And the message still verifies normally. Let's explain how we did this, how this proof of concept works. This is like a simplified version of the parsing code of GPG, where it just loops over all the packets, and a normal detached signature would just look like this. The signature file itself would just be a signature. It would see this is a signature, and then have seen equals 0, which GPG mostly uses to say, I have a detached signature to verify here. And if you would pass a full signature, it would work correctly, because you would first have a metadata packet. The metadata packet is not a signature, but it's also not a plain text. Scene stays 0. Then you would have the plain text, not a signature, but a plain text, so scene is set to 1. And then you have a signature, and the thing is then not verified as a detached signature. So that's all good. However, if we add this other packet type there, which is just a PGP magic byte marker, just literally the string PGP in there, it's also not a signature, but it's also not plain text. It's a different packet type. Scene gets reset to 0, and we print what the plain text packet specifies, and was copied into a buffer. But we verify it as a detached signature. The fix is rather simple. Instead of being able to reset this, we just use the fix is just to use or equals to never reset plain text scene. The impact is multiple plain text attacks on detached signatures, allowing marking unsigned content as verified. And we reported this, and it was fixed with our exploit payload in the commit message. However, it's not in the current release yet. So recap so far: we broke the clear text and full signatures in multiple ways. Also, detached signatures are spoofable in this way. PGP alternatives also have some issues. So let's take a break from signatures and move to a bit of a philosophical question. Is crypto on the command line even a good idea? And we say that as people who probably spend most of the days in command lines, right? So I guess the first fun thing here is all my crypto CLI tools display ANSI, which is what Lexi used to make her key. But you can, of course, also do more malicious things, like saying, oh, there's like an update available. Some CLI tools do that, and then you just go there and download the thing. OK, yeah. We don't want this because ANSI is able to kind of move the cursor arbitrarily, change colors and more, and then kind of write things and overwrite things in kind of areas that we would kind of first assume to be trusted. And what should actually happen is what the GSIP utility does is to first ask the user before outputting untrusted binary to the terminal. OK, the kind of the most impact we found for this was actually getting users with like a pretty much plausible user interaction to get code execution. The RC specifies a file name field for the plain text packets. Basically, if you decrypt it, it should be stored there. And GPG interprets this as a file path, so you can put any path the user can write to. But GPG will ask you before that, and all it takes is just to press enter. So if you would see pts.enc and asks you to decrypt some untrusted thing to my home folder.bash complete, I would say stop. No, Control C, I don't want that, because that would give me code execution, right? If you could get a user to execute this chain of commands, we use ANSI to override this into like a totally harmless sounding message that you could like, yeah, of course I want to see this in safe mode, enter, but actually you kind of got click checked in the terminal to overwriting a file, allowing kind of allowing code execution, for example, printing this string here, but also, of course, you could do a reverse shell instead. GnuPG addressed this issue by changing the default of the output file name, which mitigates this issue, but we would still love to see implementations asking user before outputting binary to the terminal. We recommend using a GPG version that includes this patch to user. If you need one more argument for why not to use do that, you don't want to have Rick Astley appear in your trusted UI. I guess there's the meta question on trusted UIs. What's that even? All right, back to Lexi for another PGP alternative, H.
Okay, so actually we don't have entirely bad news. Some actually handle things well. For example, the H encryption tool is an alternative to PGP encryption. It's a simple, modern, and secure encryption tool. To quote Zoatok Dreamseeker, H is what PGP file encryption would be if PGP didn't suck shit. It's basically, it uses modern cryptography. It has Rust and Go implementations, even a plugin system, etc. And it's basically the recommended use for like encryption things. But the question is, why is this in our talk? And this all started because I was trying the YubiKey plugin, and if we just encrypt something to a YubiKey plugin, or at least it used to be like this, we try to execute a plugin by just searching in the $path for H plugin YubiKey. I was not quite a fan of this. I complained online about this. Basically, why is it trying to run random binaries derived from the public key? So actually, let's look at the specification, if that's supposed to happen, and turns out yes. Basically, the plugin system for H specification specifies that mapping recipients and identities to plugin binaries works like this. Plugins are identified by an arbitrary string name. This name is basically just one or more printable characters. And when a plugin recipient is provided, the client searches for a binary with the plugin name. And this is where I got a bit curious, because an arbitrary vchar, so that also includes strings like this. So, for example, this is a big oops. For example, if we just run an strace on the right recipient here, this happens. It tries to call H plugin exploit // bin /pwn. And actually, yes, that calls the binary. So basically, we just executed a binary that we did not want to execute by just trying to encrypt something to a public key. The disclosure was also quite fun, because all of the GPG disclosures were, of course, GPG encrypted. So the H disclosure, of course, has to be H encrypted. The problem is H very heavily recommends using one-time ephemeral keys, so like no long-lasting credentials in case those get pwned or anything like this. So what key do we use? So I just looked at the socials and stuff where to contact someone, and I actually found, they're live on Twitch. I just went into the chat and asked for a public key there. And turns out the disclosure was really fun and worked perfectly well, and the patch was actually released really fast. Basically, the impact was recipient names can contain arbitrary path traversals, enabling arbitrary binary execution. And it was fixed in every implementation and even updated in the specification. It now includes that a name must only contain alphanumeric and a few special characters. Relatives paths must not be searched explicitly, and plugin names must not contain path separators. So the recap so far: signatures, severe bugs in clear text and detached signatures, crypto on the command line, bad idea, and a lot of CLI tools have vulnerabilities there. What about memory safety, though? And for that, back to Liam.
Yeah, we should have, this is an interactive talk, by the way. We should have registered this actually as a game show. Sorry for that. The question for you here is, if you look at this GPG code, can you find the bug in here in the ARMOR filter implementation?
Just raise your hand if you
kind of the first thing. If you see I got a bit of a head start, you can raise your hand. I just showed you the heading. It gives something away. It might be something about copying the data in like a slightly faster way. Yeah, I see some hands. Yeah, this is the thing that copies the data. Yeah.
A few more hands.
A few more hands. So what makes a thing blazingly fast? Yeah, we increment n both in the loop header and in the loop body, which is kind of a fun thing to be kind of in the main ARMOR parsing function. But I guess it ended up in the low. We have like a shared pad, and it ended up in like a pad called lower prior issues. Because I mean, just looking at this code, okay, it's not correct, but like the best you can get is for half the inputs a 1-byte override. Okay, it's not so interesting maybe. But then Lexi looked at this again. It's like, oh, and it's also used as a return length here. And then if you concern yourself with how GPG processes data in so-called I/O buffs with filters, you notice that you should never return more data than was requested. So in this case, if we return more data than was requested, we get an like integer overflow of an unsigned int, and we can like multiple places where this is called read much more than we have and potentially get some exploitation primitives from it. The next thing was, how could this even be reachable, right? Like, I mean, this is there and apparently never caused issues. And also, if you see like input bypass and see what it kind of appears to be doing, it should kind of only be true for for binary data, so especially not for base 64 encoded data. But then the ARMOR filter is only pushed for base 64 encoded data. Both use check input to see if this is reachable. So we would kind of need a Schrödinger's payload to get this double increment loop run with binary data. And the simple fix is, again, looking at how these I/O buffs work. They process data in chunks called overflows, like not bad overflows in this case. And if you supply enough to overflow the filter, it gets called twice with different inputs. And then the only thing we need is, in the meantime, find a gadget that resets int bypass for us. I will go over this quickly. This is kind of the control flow sketch showing the autonomy of this payload that we ended up using to trigger this. We have a normal ARMOR header, then some base 64 encode, then some base 64 data. So we push our ARMOR header, we set input bypass to 0, so far so good. And then we read, but however, this data is so much that it fills a 64 kilobyte buffer when decoded. So we get our first, we get our next chunk parsed, which then exactly falls on this marker packet for an optional CRC line, which is just a thing you can specify. And this then checks the input again and sees no ARMOR, and uses input bypass for something slightly related, but not the same thing, just reuses the variable, but has a safe version of this copy loop, this mem copy loop. So we need to supply so much that this thing also needs another chunk. And this other chunk is then processed by our ARMOR filter function that we then call with input bypass 1 and non-empty buffer, and we get the double increment loop to run, as you can see here in GDB. Yeah, we reported this, got a good response from the maintainer of the project. They pushed a fix in this commit message, including our proof of concept on the dev branch, and also they improved their I/O buff filter system to now always runtime assert that you didn't read more data than was requested. And we recommend GnuPG users to use a GnuPG version that includes this patch. One more C issue, this time very, very easy to spot. There is just an uninitialized variable, so this at this point can contain anything. And in some situations, it's used to say, is this a self-signature? And we use this to allow the SHA-1 digest only for self-signatures, because we don't want to have third parties use a digest with SHA-1. However, this variable is uninitialized in some branches, so yeah, you can actually reach here. We also reported this bug, and it was fixed. We recommend users to use a GPG version that includes this patch, and we recommend implementations to use sanitizers like Memory Sanitizer with a comprehensive test suite, plus static analysis to catch such issues. All right, back to Lexi.
Okay. So the next vulnerability has to do with message malleability. So this is basically just being able to write into an encrypted message without actually knowing the contents. So for this attack, we'll just describe the threat model here. For example, we have an attacker called Mallory who just basically sends you a message saying, hey, I encrypted my public key for you. Can you upload my key to a key server? So just an encrypted public key. Okay, so we just use GPG-unwrap to extract the public key out of there. It actually has a small error message saying decryption failed, invalid packet, but if you actually look at the output of GPG, it's a valid key. This looks like your average key, nothing wrong with that, so this actually decrypted correctly. So fair enough, let's upload that to a key server, and if you just uploaded that to a key server, you just decrypted something with your own private keys directly to Mallory. So how this works is basically GPG has checks, so malleability is not possible. So if GPG actually does detect malleability, it says, warning, encrypted message has been manipulated up there. But the thing is, this if condition only checks for error bad signature and error truncated. But the thing is, we can just do some things like putting an irregular AOF in there. And if we put an irregular AOF on there, it throws GPG error invalid packet, which fair enough, then prints decryption failed, invalid packet, because you'd think one of the packets is broken, but no, it turns out that completely suppresses the warning encrypted message has been manipulated warning. And because GPG first prints what it just decrypted and then does the check instead of the other way around, this just completely works. And the thing is, the actual exploitation is quite hard because we can only modify one of these 16-byte blocks. The thing is, these 16-byte blocks, at least the first one, is already pretty predictable because it's almost always a CLib decompression packet and always has the CLib header in that. So we can just guess those bytes and do malleation with just a simple XOR there. What we do is we replace CLib with deflate for the simple reason that deflate doesn't have this header. So we can just write an actual PGP packet in there. And what we do is we start a comment packet, which basically just catches all of the errors we will just cause in the next block. And after the next block, we just basically resume decryption like normal. So this just decrypts everything that was originally decrypted into this comment packet. Okay, no, it's in the comment packet. That's not enough, though. What we now do is, first of all, since we can only modify one of those blocks, we actually abuse another bug in GPG that actually can disable the decryption layer by putting an EOF in the right place in the packet. And then we just start a normal public key packet. This is the one we've seen earlier. And in this public key packet, we just introduce a normal key server field. And in this key server field, we just start with our evil URL. And then we tell deflate, because we are in a compression algorithm, we can just tell deflate, hey, look back to this position. And in this position is the actual decrypted plaintext still in our buffer. So deflate can basically read that back and put it into that key server field. And if we do this and actually look at the keys that we just sent to a key server, we can see preferred key server, HTTPS localhost 999, upload key. And there's a bit of binary data in there. One of the things is the CLib header that's visible in there. But a bit later, there's the actual plain text of the message we did not intend to decrypt. So just that is plain text in the message there. You can also view this key yourself. This is basically how you can exfiltrate something that someone just accidentally decrypted to you. So the impact of this is basically a malformed OpenPGP message can bypass the integrity protection checks, and an attacker can just steer the packet parsing in there completely to exfiltrate plain text with, basically just exfiltrate plain text bytes that you didn't intend to decrypt. This is actually closed as a won't fix because the GPG team says, yes, there was an error, the invalid packet error, and that is enough to tell the user that they shouldn't interact with this. We don't think that's a correct fix and that this should be fixed, but they won't fix it. Recommendations for this, basically for implementations, just have stricter error parsing, or for example, check that the checksum matches before outputting the actual output, like for example H does. And for users, treat all warnings that GPG prints as errors. You cannot predictably tell if something has gone wrong with an error message because we can just manipulate the error messages. And another thing we'll present is to trust or not to trust. Basically, you might have heard of trust chains like this. For example, if you signed Alice's key, if Alice signed Bob's key, and if Bob signs Carol's key, we can trust Carol because there's a chain of signatures. This always starts as your own key in PGP, but the question is, how do you trust yourself? So, for example, GPG has to know which key is your key. And the PGP specification actually has something for exactly that. That's the trust packet. Trust packets basically contain data indicating which key holders are trustworthy introducers, so which keys are yours that can sign other keys. And this format is defined by implementations. And it should not be emitted to output and should be ignored on any input because otherwise someone can just add a trust chain to your keychain. The problem is GPG doesn't do that because there are two options that actually allow doing this. Those are the --keyring option and the --import option restore options. These sound safe, and they do not say in the description that they are wildly unsafe, but they allow using and importing foreign trust packets. Plot twist, this is widely ignoring the RFC, but doesn't actually affect GPG's trust model because they have trust packets. But if we look at the actual implementation of trust packets, note trust val is not yet used. So the thing is, GnuPG uses a separate trustdb.gpg file and does not actually store trust values in trust packets. The question may now come up, what do they store in trust packets then? And that's the important bit. If we look just a few lines below this comment about trust val not being used, we can see the following code. If sigflags.checked is true, then we set the sig cache of trust packet to 1. And if the signature that we processed has the valid bit set, we set the signature cache to 1 and 2. The signature cache? Uh-oh, that sounds bad. And apparently, the trust packets contain a signature cache bit, but surely we don't blindly read those back, do we? So if we actually look at the code in parsePacket.c, it gets the last signature from the context by just doing context last packet signature, so now we have the last signature packet, and then it reads the trust packet sig cache byte, and if that's set, if the 1 byte is set, we set checked on the last signature, and if the 2 byte is set, we set valid on the last signature. So we can basically just write an arbitrary number into a packet, and then by just writing a number there, we can just set the last signature to valid. But the thing is, where is the signature cache actually used? And if we check the actual function that handles text signatures, so the thing that you use with GPG-verify, that doesn't actually use that. That actually gets the public key, that actually makes sure that the signature is valid. So signatures over text do not use the signature cache. But where is the signature cache used? There's another kind of signature. The other kind of signature is the key signature. So that's things like signing subkeys, key revocations, user ID certifications, and things like that. And that just reads the sigflags.valid, and if that is true, it just returns 0. So OK. So TLDR, if we forge a trust packet with just putting a bit in the right place, we can set the checked and valid flags on a key signature, which allows a couple of things, like adding signing subkeys. We can add authentication subkeys. This is the thing that happens if you use GPG with SSH. We can add encryption subkeys. We can sign other keys, and we can revoke other keys. So to really drive the point home, we have a few proof of concepts. The first is Governicus. You might have heard of Governicus. They work with the German government and offer various government-related ID things and products. And one of the things that they offer is the Governicus PGP service. This is also on behalf of the BSE, so the German Federal Information Security Office. And what they can do is they can notarize your OpenPGP key. So what you can do is you basically just give them access to your online ID for a moment, and then they sign your PGP key and say things like, this is proof of your real identity in the digital world, and administrative procedures or business matters can be carried out easy, safely, and quickly, and at any time. So this basically requires someone's ID card to sign a key. So let's forge one of those. So we start with this, where we import the normal Governicus key, import this into GPG. This is the normal key. We added it quickly to give it access and trust, so it can verify other signatures. So this is just the normal procedure. And then we import our own key. And then we do GPG-check signatures. And GPG tells us with full confidentiality that we are Angela Merkel and had access to Angela Merkel's the government ID. We obviously did not. So the next proof of concept is a bit fun. We do some revival. What's like the most well-known PGP key, we asked ourselves, and one of the things that came in mind is the one of Satoshi Nakamoto. That's the Bitcoin inventor. The thing is, we presented a bunch of signature validation bugs, so can we use one of those to just forge a signature for him? Turns out, no. Satoshi's the edge case, nothing works. The previous vulnerabilities all modify existing signatures. The thing is, Satoshi has never signed anything. He just published his PGP key. There is not a single signature on the entire internet. We looked. So let's give Satoshi a new signing subkey. So what we do, we import this key, that is Satoshi's key, and then we just decrypt this message, and this message says, Bitcoin is backdoored, get out while you still can. GPG.fail. It says, good signature from Satoshi Nakamoto, but this is not certified that this is the right owner. But if we look at this fingerprint, this is the actual Satoshi fingerprint. GPG has basically just showed us that Satoshi has signed this message. And spoilers, Bitcoin is actually not backdoored as far as we know. You do not have to sell your Bitcoin right now, but if we just posted this on Twitter with no comment, we could probably crash the Bitcoin course as well. And another proof of concept, we can just do a backdoor. So the thing is, we can just import a packet like this, and if it's imported, it just stays there. So we can just also, with this, permanently backdoor encryption. So let's just create a key that backdoors encryption to the CCC disclosure inbox for any security research in the audience here. So this is very easy. We can just do this. We encrypt something to our key. It even says here, yes, this is the right key and everything, even the subkey fingerprint matches and everything. And what we now do is this. We just use our key that we generated for this and just decrypt the same thing again. This is basically just permanently backdooring encryption for anyone who imported a key like this. Yeah, and this is the Keyring signature cache bug. Basically just using --Keyring or --import options restore at any point imports untrusted trust packets into your Keyring and basically permanently reduces the authenticity of signatures. The status is we reported this 2 months ago and it is still unfixed. Recommendations basically for implementations: don't do things like this. Don't use a signature cache that users can set. And for users, never, ever, ever use import options restore or --Keyring. Those are very dangerous with untrusted files and basically ruin the entire trust model. And yeah, to finish this up, here's our GPG Wrapped 2025 in review. Some numbers. Vulnerabilities found is in total 14. That's a lot for 1 year. Bugs affecting signatures are 9. Signatures all the way down. Unpatched issues, 9. That's a lot of 0 days dropped on stage. And Git commits signed by GnuPG, a total of 0. Not really inspiring confidence. And the oldest issue, the oldest commit containing an issue that we found is from 1999 and was committed before the speakers were even born. And that's a wrap. Thank you for listening. Here's an overview.
Thank you very much. You even left time for Q&A, which is awesome. So, do we have questions? If you have, line up at the microphones, you know the drill. For the microphones at the back, please wave so I can see you because it's rather far away. We have a question at microphone number 1, please. Come close to the microphone.
Is there a particular reason that the GPG...
Closer.
This type of microphone is a little different. There we go. Is there a particular reason that the GPG developers don't sign their own commits with GPG?
I have to ask them.
Good question.
But, I mean, yeah, Git has some security, but it would be nice to see that for using their own tool.
We'll add it to the request for comments for the op-ed.
Microphone number 4.
Yeah, what has been the experience of reporting stuff with the GPG people? Do they engage with this? Or, like, there's so much unpatched stuff. Like, I assume they have to take it seriously, but what is going on there? Can you shine some light on this, or do you want it to stay confidential?
I guess we can say a few words. Send the emails out. Some we got like very quick and positive responses from the GPG teams. Others we didn't. Yeah, some were won't fix, which I guess you can have different opinions on some of the visual stuff, but we would still love to see that fixed. Yeah, but I guess we would love to see all that green.
Like the communication was nice. They were kind, but the actual fixes were either like they fixed some things, but the things they didn't fix, there's basically just not been any communication there.
Yeah, and I guess another thing could be, I guess you can also have different opinions on full disclosure or not, but like me personally, I wouldn't commit proof of concepts to the dev branch, but I guess any project can do this as they want, and you can choose what project you use.
Like, for example, the memory corruption thing was pretty hard to exploit. The actual bug was relatively minor, but the actual exploit chain to get there is pretty long, so just not committing that would have done a lot for security, but they just committed the entire thing in the commit. So, yeah.
Microphone number 1, please.
Hello, I'm the developer of AGE. I wanted to thank you for reporting an issue, and I wanted
Thank you for making the tool.
And I wanted to hand deliver the AGE bug bounty and a few stickers.
Sure. Hi. Thank you for making it.
I think we can all agree this is the way how bugs should be addressed, including stickers. Any further questions? We have something on the internet, please.
Yes, the internet wanted to know 2 things. One is, will the slides be available?
We'll make it available after the talk, yeah. Also, GPG.fail should be live. And
Okay.
We'll put the slides up later.
And the other is, did you get in contact with the BSI? Because GnuPG is approved by BSI for restricted information.
We considered, but we just reported this to the GPG team itself because they are the ones making the software. They are ultimately responsible for it. They get a lot of funding by BSI, so we just assume that they communicate with them, but if they weren't involved, that's not really our responsibility. We just disclosed it to the developers.
Thanks.
Any further questions? Last call? Anyone? Anyone? Bueller? Well, then in that case, please give another very warm round of applause to Liam and 49016.